Okay, welcome to the 15th class meeting of the spectrally correlated random processes. Okay, let me check the check. Okay, so we were covering this 20th journal paper, asymptotic fresh proporizer paper, and we skipped many proof parts and also found that the main proof of this discrete time version relies on the continuous time version. So here, this reference 27 of this paper, I checked it and pasted it here. And it's all about, as I told you, continuous time version. So you can find the proof for the continuous time version. The problem of this paper is that this conference paper and this journal version have a little bit different equation. And it seems that there is a typo here, I believe. Or I define the complementary autocorrelation, the Fourier transform of the complementary autocorrelation a little bit differently. So if you see the bi-frequency spectrum or bi-spectrum of the improper complex cyclostation random process, this direct delta component shows that the impulse frequencies are going upward to northeast direction, and also the complementary autocorrelation goes to the northeast direction. But actually, if we exactly follow the notation of journal 20, this should be positive. Okay, so I've already started to write down the second take-home exam, and second take-home exam is to prove some results, and where I especially emphasize that this should be positive, something like that. And just take a look at the problem of the take-home exam 2 and follow the definition there. Got it? So sometimes the conference versions and journal versions adopt different definitions, so be careful. Got it? Anyway, basically the proof is just the same, almost the same for the continuous time version and the discrete time version, except that discrete time Fourier transform is always periodic with period 1 Hertz. Got it? So be careful. So the main proof of this paper is also omitted. And let's see the result first, the result again, to see the importance of it. So here is a discrete time cyclostationary random process with, in this case, cycle period capital M. Got it? And you have two branches. And the first branch processes the original random process x of n, but the lower branch takes the complex conjugate and then processes. And here, if you take a look at these two blocks, they are identical and have the discrete time Fourier transform sketch it here in figure 1. So since this notation is not good, if I write the paper again, probably I would specify in this way so that you can recognize the Fourier transform is the discrete time Fourier transform. But since having the exponential function and putting argument in the exponent is cumbersome, so I just defined the DTFT as capital G sub M of F. Okay, so this is DTFT, not CTFT. And DTFT is always periodic with period 1. So we just need to focus on this main period. And here, subscript M means that you divide the length 1 interval into M subintervals. So 1, 2, 3, and M. So each interval is of length 1 over M. However, unlike the fresh vectorizer, your passband within this subband is only half of it. So you have this length 1 over M, and only half of the band is the passband. And so you have capital M passbands within a single period. Got it? And this is repeated due to the periodicity of DTFT. So your upper branch takes the frequency component on these subintervals, and the lower branch after conjugation, so the frequency contents on the other subbands are what? Are flipped. Because if you take the conjugation, then what happens? Your output DTFT is the original DTFT's complex conjugated and frequency reversed version. So this will appear here, that one will appear here, right? Something like that. So again, the other frequency band components pass through this low pass filter. And the difference is that this just passes through, but here you down convert, so frequency shift by 1 over 2m hertz. What does that mean? Here, the frequency component at 1 over 2m now shifts down. So entire frequency content at this point is circular left shifted by 1 over 2m. So again, the frequency components at here appears there with flipping and shifting. So this one goes there and moves down here. Of course, as I told you, this is not the unique choice of fresh properization. You can develop the method that just flips here and take conjugation, and flips here and take conjugation. That kind of fresh properizer also works to make the output a proper complex cyclostationary random process with cycle period 2m. So here, this is not only proper, but also the cycle period is doubled. Got it? So whenever you do some graduate level study, especially in signal theory and optimizations, first, never forget that the uniqueness, you need to check about the solution. In many cases, no unique solution exists. There always exist countably infinite number of solutions, as we've seen in solving this very simple optimization problems, right? So what was the solution when R is Hermitian symmetrical and positive definite matrix. As you remember, Rayleigh's quotient, this is simply Rayleigh's quotient, and the solution is what? Some non-zero multiple times the eigenvector that corresponds to the maximum eigenvalue. So what does that mean? By taking any complex, non-zero complex number, k, you can achieve the maximum value of this Rayleigh's quotient. So not unique. Of course, you can define an equivalence class and saying that there exists unique optimal solution in the sense, under some sense of equivalence. However, sometimes you even do not carefully examine the existence of solution. This is more problematic, and we sometimes just assume there exists optimal solution, but sometimes it is not guaranteed. However, most of the engineering problems are not looking after the exact global optimal solution, but we are mostly satisfied with some locally optimal solution. So in that case, this is not that important. However, to provide or fully characterize your solution to the problem, never forget to check the existence and uniqueness of your solutions. Got it? Sometimes, without checking the existence, you may have difficulty because there is no solution, but you are trying to find one. Sometimes there are many solutions performing the same in terms of the performance metric you have chosen, but they may perform differ in other under other performance metrics, because we sometimes cannot put all the optimality criteria into one problem, because if you have more than one optimality criteria, then your problem becomes multi-criterion optimization, and it's very hard to find or fully characterize a solution in general. So what we do is that we choose one of the optimality criteria and try to find all, not unique, all possible solutions, and then we examine each optimal solution using another performance metric. Or sometimes we combine two performance metrics with some weighting, alpha times some performance metric plus 1 minus alpha times another performance metric. That is called so-called scalarization. But sometimes this scalarization approach is too much abused because people cannot find, cannot fully characterize the optimal solution. So anyway, that is another way. Sometimes we not only just combine two performance metrics, but just use some value lambda, usually called the penalty coefficient, and just add that penalty to our performance metric objective function. And that is actually almost the same as this scalarization, because anyway, in optimization, non-zero scaling of our performance metric doesn't matter. Got it? So penalty method and scalarization, actually, they look at the same approach. Anyway, I'm not going to spend too much time what happens when you do not examine uniqueness and existence of solution. But anyway, I want to to very much emphasize this non-uniqueness of fresh preparizer given our problem. Got it? There could be many methods. For example, you just flip and conjugate frequency components in this subinterval and flip and move here, right? And flip, move there, something like that. You can do that. Or you just circular shift the frequency components. So there are actually, given the m subintervals for the passbands, actually you have m factorial method to design your own fresh preparizer. Got it? So what I have shown here is just the one out of capital M factorial combinations. Got it? Anyway, one of the reasons why I have chosen this structure is this conjugation of the entire observation is a common practice in the so-called widely linear or linear conjugate linear signal processing. So let me give you some terminologies which is very important and has been used in this complex signal processing. So first, you know what is linear filter. What is a linear filter given some observation y of t or y of n or vector y? What is linear filter? So let's start from the vector observation case. Linear filter means that, okay, let's use x, okay, for the input. So you have x, and here is linear filter, and you have y. So in this case, y equals some, what do I say that, fx, and f is a matrix or row vector if you want. What about in discrete time or continuous time case? We already know linear filter gives us what? Impulse response with two variables. And similarly, we have the formula for the discrete time. Now, what is then linear conjugate linear filter? Abbreviated as LCL filter. LCL filter is simple. Just you take the observation and take the conjugate of it, and then perform linear filtering. Sometimes you have a simpler version. Like this, depending on how many outputs you want, right? Here, obviously, in this case, you have single input and two scalar outputs. So sometimes you add them up and generate the output. In that case, it's not that difficult that these two structures are the same. You may just view it as hey, I have two input and single output, so this is what? This must combine two signals after linear filtering. So you can show that if you have some linear filter, 2x1 input, and then there exists one input, one output linear filters in the lower branch, something like that. And this linear conjugate linear terminology has been used for cyclostationary signal processing society when they processed complex valued signal. And almost the same idea has been used in complex signal processing guys. They didn't much thought about cyclostationarity. So in their case, their observations were usually a complex valued random vector. And they had two approaches, as I told you. One is to take the real and imaginary part and do the linear processing to have some output. And another widely linear filtering is to what? To take again the conjugation of it and do linear filtering to have the output vector. Of course, as I told you, the output could be a scalar valued complex number. Now, let's take a look at why the linear filter in this structure is same as why the linear filter in that structure. Anybody? So the equivalence proof starts from this observation. Suppose you have some complex number z. What is the real part of it? By using complex conjugation. And what is the imaginary part? Imaginary part is simply z minus z conjugate divided by 2j, where j is the square root of -1. Okay? So the upper branch is nothing but what? So the upper structure, again, what? Actually has the conjugation operator. And now you can group these all together because anyway, they are all linear. So this block corresponds to that block. Got it? So mathematically speaking, if your widely linear filter that has this structure achieves some optimal performance, then the widely linear receiver having this structure, the lower structure, must achieve, the optimal one must achieve the same performance. There must exist an optimal widely linear filter that has this structure. Got it? So do you see the commonality between these two? They all have what? they all have the branch that copies the observation and takes the complex conjugation. And of course, you don't need to always take the complex conjugation for optimal estimation and detection. So be careful. Sometimes many researchers and even I got confused whether this front end is necessary or not for an optimal processing of the signal. And naturally, that question is stupid because anyway, all the information in X is contained in X. So the natural question is that so this is not necessary. If you really need to take conjugation, anyway, your optimal processor, here, an optimal processor in some optimality criteria, even without this part, will automatically have conjugation operation. So, by the way, let me be careful. So, this one will have some conjugation operation. Then why we start with this structure? Because we are sticking to linear filtering here. So actually, the reason why we have conjugation operator in front of all the other filtering is that we are sticking to linear filtering. Because what is a linear filter for some complex random variable? As I told you, we have some, did I use A? What did I, F, okay. What is this? You have complex valued column vectors and just elements of X. No conjugation, okay? So linear filtering that admits complex random variable, complex valued input cannot have conjugation operation. What does that mean? These operators or that operator is not linear. So it's kind of very weird. That simple operation, taking the real part, is not a linear operator. Got it? Then what can we say? We may say that a conjugate linear operator. So that's why we have this front end. And why we really need this? Because we love linear processing or affine processing. So we want our receiver structure linear or affine function of x. However, in complex valued signal processing, this may not perform well. So what we do is that we augment our observation with its conjugate and then perform linear or affine filtering to have better performance in some sense. And let's see why this is true. And actually, the simplest example is too trivial, so you will immediately see why that is so. So suppose you have observation, complex valued observation x, that is data b times e to the j theta plus noise. Here, noise is just a second. Let me be careful. Yeah, noise is Ni plus Nq, where Ni is independent of Nq, but Ni is real Gaussian with variance sigma, and Q has the half of its power. Got it? So if we plot the scatter plot, assuming we have IID such observations, what will happen? This is real of y, and this is imaginary of y. And if theta is this value, we will have what? No, okay. Yep. So we have the value of realization of y that has more spread along the real axis than the imaginary axis. Got it? Now, the question is, what is the performance of the linear receiver to minimize the mean square error? So here we assume that B is random with equal probability. So the first one is that let's consider a linear filter that minimizes what? The mean squared error between our data B and its estimate, linear estimate. So linear estimator must process y, which is scalar, by just scaling. So here our solution, let's say W, will minimize this quantity. Unlikely widely linear filter will minimize what? B minus some W1y minus W2y conjugate squared. Got it? Do you see the difference? So here, this is the linear filter output when you have scalar input and scalar output. Why do we have scalar output? Because that output must be an estimate of B, right? And here we have that one, W1y minus W2y conjugate. And if we put parentheses, then you see that this is what? This is a linear filter output when you have two inputs. One is y and the other is y conjugate. Got it? And if this sigma square were not different from sigma square over 2, so suppose the noise is circular, then you will see that they perform the same. And you can find some optimal W that is same as W1, and you don't need conjugation. However, if theta, in this case, theta is not 0, is not half pi, is not something like this, if I remember, then you need this y conjugate to lower this mean squared error. Got it? So this is the mean squared error when you have a linear receiver. This is the mean squared error when you have a widely linear receiver. Got it? Anyway, this may appear, this simplest example may appear in your take-home, so enjoy if it appears. I'm not going to too much delve on this problem, and you will find it fun. Anyway, so I covered the terminology widely linear something and linear conjugate linear something. Another one is fresh filtering, which, okay, question?
와이들리 리니어로 확장될 때 그 와이들리라는 표현 안에 컨주게이트 오퍼레이션이 들어가기 때문에 그런 겁니다.
Okay, so good question. The question is why the name widely linear is widely linear. So the reason is very simple. Actually, widely linear is, precisely speaking, is not linear. So whenever we have some wide or narrow, then what does that mean? Wide sense something is actually, precisely speaking, not that something. We know stationarity, which is usually, which must be defined as strict sense stationarity. So wide sense stationarity, for example, is not stationarity, or what you want to do is that you want to somewhat make the notion bigger than before. So this wide or widely is quite often used when you want to little bit expand the already established notions, or you want to generalize the notions. So everyone will say that linear filter for a random vector x must have this structure. However, in widely linear filtering, you have what? After you augment your observation with its conjugate, you may say that it's a linear filter. So it's a linear filter to this augmented observation. But precisely speaking, it's not in this form. That's why people wanted to use this adjective wide, but we already have another adjective, so this adjective now became adverb widely. That's what I believe, okay? And also, when I coin a terminology myself, I also follow this type of approach. Got it? So it was a very good question. Whenever you have a question about the terminology, sometimes even though your understanding is not exactly following the historical development, that doesn't matter. as far as you have a logic, that is good. Anyway, when we, for example, teach or when we copy that idea of expansion to another situation, your, how to say that, rewritten history in a logical and orderly way serves better, actually. Got it? So if you really want to be a historian in electrical engineering, I'm not going to stop you, but yeah. Anyway, so it was a good question. So let me move to this fresh filtering, the terminology fresh. And I already told you that this is coined by Dr. Gardner, one of the pioneering researcher in cyclostationarity. And this is from frequency shift. So fresh filtering is a filtering that involves frequency shift. So for example, as you've seen in my structure of fresh properizer, what did we have? Why I called it fresh properizer? Because we have here the modulator that shifts the frequency. So in this structure of fresh properizer, what is the frequency shift part? This one. Got it? So whenever you have actually some modulator, then you may say that you are doing frequency shift filtering. And also you may wonder, okay, why do we need this terminology? And let me tell you. So suppose you have linear filter. And linear filter is, as you've already seen in the first take home, always have two parameter impulse response. And your filter, linear filter, that takes the input X, has this structure, right? So this is the most general linear filter structure. You just have two parameter function. However, we have one extreme case, very, very special case, that is called linear time invariant filter, where what happens? Our impulse response is same as what? This one. So actually, our impulse response does not change even we change the time origin 0. Okay? In that case, we may redefine this one as a single variable function. In that case, we have what? That famous convolution integral. Got it? So this is one of the most general structure, and this is very, very special structure. And we want to have something in between that is still linear, not linear time invariant, but similar to linear time invariant filter. What is that? That involves so-called fresh filter. That is called fresh filter. And two most important components of fresh filter is that, anyway, it's linear and has modulator. At least one. Got it? So you frequency shift your observation or some intermediate signal during the processing. Sorry, linear time invariant filters. So you may say that a fresh filter is a linear filter that has linear time invariant filter or filters and at least one modulator. Got it? So among every possible linear processing, you restrict your filter, linear filter structure to have these things only. Now let's see whether our fresh filter is really a fresh filter. So if you just look at this one and that one and that one, what? We have linear time invariant filters and a modulator, and this is again linear time invariant operator, right? So this is fresh filter. However, it has what? This one. So if we just adopt the LCL, the linear conjugate linear terminology, then this should be called what? Linear conjugate linear fresh filter, or linear conjugate linear fresh filter. But if we just say this is the linear conjugate linear fresh filter, we are very misleading the readers because there could be totally different linear conjugate linear fresh filters, right? So that's why I didn't call it linear conjugate linear fresh filter, but called it fresh properizer because this is, even though this is linear conjugate linear filter, the purpose is to properize the improper cyclostationary random process. Got it? So in the same reason, I didn't call it widely linear fresh filter because that may be totally different receiver. So fresh filter is a very special linear time varying filter. And why this frequency shift idea has become important in cyclostationary signal processing? Because as our title says, some random processes exhibit very strong correlation among some frequency components. Not every, but some. Especially one of the exemplary cases is what? Cyclostationary random process. But there are other random processes that exhibits very strong spectral correlation. Of course, in many cases, these random processes are kind of induced random processes from cyclostationary random processes. For example, consider some case where you have mobile transmitter that transmits QAM signal. However, your receiver moves very fast with multiple paths. And these scatterers are also moves very fast. What will happen? Not only you have cyclostationarity, you have some a Doppler frequency shift. And interestingly, this one's Doppler frequency shift will be different from that one's Doppler frequency shift. So let's start from our original x of t. In complex baseband, we will have strong spectral correlation with spacing 1 over cycle period. So in our complex baseband, we may have some strong correlation with that component and that component and that component and that component with equal spacing. Of course, even I just wrote this way, the other frequency components have strong correlation, right? And we may have some other frequency components having strong correlation. Now, this signal having strong correlation has what? Doppler frequency shift. And that Doppler frequency may time vary. Then what will happen? Here at this point, if this is T and this is F, what will happen? You have this component will change, right? Due to the time varying Doppler frequency shift like this. And you have that frequency component will have location here, there, something like that. And you have another one something like that. And you have another one so this time varying components also has time varying center frequency. Of course, in many cases, this scale of T will be very, very slow compared to very, very small, very, very large compared to our cycle period in general, unless it's some Warp 9 Starship or Mach 5.7, some jet flight. And another one is that here you have another component. Then what? Some other signal components will have strong correlation. So you have the summation of this random process and that random process at here. Now, for example, you want to do some estimation or detection at here. What are you going to do? You may say, I don't know what to do. But anyway, we may further simplify the situation like, okay, suppose only these components have very large components. So even though we have strong correlation, these signals originally transmitted is very small. Well, that's the true story when we have QAM signal with access bandwidth between 0 and 1. We sometimes have just single frequency component that does not have any spectral correlation with any other components. We only have some small just rank 2 interference, something like that. In that case, summation of these two will have what? Some strong components, for example, this one varies that way and varies that way. In that case, what? Probably we have some replica of this one, or at least replica of some power spectral density. And based on that information and some with the help of some pilots, we may estimate the frequency drifts or Doppler time varying Doppler frequency. And we need to compensate that Doppler frequency shift Got it? And actually, as some of you already remember, that is the structure of our joint estimator and equalizer we provided for Samsung networks, right? We have what? We had what? We estimated the Doppler frequency and what? We shifted it down, the received signal. So we did what, actually? Linear, conjugate linear, we did fresh filtering. Even though we didn't say a fresh filter for joint estimation and equalization of high Doppler environment, something like that. So people have been doing this fresh filtering from the beginning of mobile communication. Even if we have single pass from satellite or Sputnik, for example, probably you remember the history. They listen to the signal, just the beeping signal from Sputnik, the first satellite, man-made satellite, artificial satellite, and US engineers could see where it is from the Doppler frequency shift. And at that time, probably our auditory system did some fresh filtering. But anyway, after that, they developed the radar system and other systems that actively utilize this one. However, the fresh filtering has become more important in cyclostationary signal processing because we have strong correlation between these components. For example, at least the two components are strongly correlated. In that case, sometimes you need to shift not only to compensate for your Doppler frequency shift, but also you need to shift by integer multiple of cycle frequency. And sometimes even you do correlation. For example, some suboptimal structure would be something like this. You receive a cyclostationary signal plus noise. And then what you do is that you just perform LTI filtering on Y, and you frequency shift by cycle period and frequency shift negative by cycle period, and you do linear filtering and then combine to do some estimation, or sometimes you take the sample to do some detection or something. And now, what is this one? You've seen already, right? Fresh vectorizer has almost the same structure. Got it? So this frequency shift operation is very important. And sometimes it provides you suboptimal, just kind of ad hoc receiver structure. But if you cleverly choose this frequency shift amount, then what you need to do is to design just linear time invariant filters, which are the theory of which has been developed for a long time. Got it? So whenever you have strong correlation in the received signal, and also your linear processing does not work well, then of course the one way is to pursue some optimal receiver structure. But sometimes the optimal structure looks too difficult to find. In that case, just try to do this one. Even for this one, you can do something like this. Suppose y of t is the received signal at here in the airplane. What you do is that you compensate for the main Doppler frequency shift. So here, becomes do you understand what I mean? So you try to find the time varying, of course, slowly time varying Doppler frequency shift and compensate for this one, right? And then you try to compensate for the dominant. So this serves as F0t, and that serves as F1 of t. Got it? Do you understand what I mean? So this type of ad hoc structure may give you some better performance. You may have other branches from this frequency and that frequency from the original cyclostationarity that gives you spectral correlation. So I'm not saying this is optimal, but this may be the simplest approach than next to just the linear filtering. Because as you've seen, as almost all of you are my research assistants, and while we do some signal processing in high mobility, we already had the difficulty of multiple paths with different Doppler frequency shifts. Sometimes just thinking about definitely suboptimal structure may give us improved performance. Got it? So this may be a good idea even when we do some end-to-end processing. For example, we try to estimate the strongest path Doppler frequency shift and provide that, which means that you not only just provide the DMRS information, but you just provide the main path Doppler frequency shift as the input to your end-to-end neural network. And then may significantly improve. Nobody knows because these AI ML models we never expect what will happen. But sometimes that kind of clever idea dramatically improves the performance. And we've seen some of similar occasions already, right? So exploiting spectral correlation is not just a very small society's so-called otaku type thing, but it could be a breakthrough in some open or hard to difficult to solve problems. Okay, so I've covered the terminology linear conjugate linear and widely linear and frequency shift filtering. And these three, if you have a clarity in understanding what these terminologies mean, then you may have much less reduce the burden when you read other papers in this cyclostationarity papers or widely linear processing papers. Got it? Now, what is left before the end of this today's class meeting is cyclic water filling, which I didn't cover when I had to cover it when we studied this paper, Journal 18. And here, probably you already started to forget what was the problem is that we wanted to find out what is the capacity of an additive Gaussian noise channel that is done by Shannon, but slightly modifying the additive Gaussian noise as a what? Cyclostationary Gaussian noise. Why did we do that? Because many man-made signals often exhibit cyclostationarity. And not only cyclostationarity, sometimes man-made signals exhibit impropriety too. That's why we modeled the observation as this one. We have input LTI filter as Shannon did, and improper complex cyclostationary Gaussian noise. And in the previous class meetings, I emphasized how to convert this simple problem with single scalar valued input and scalar valued output to a multiple input, multiple output signal model. How did we do that? If the noise were proper complex Gaussian, probably we applied fresh vectorizers only. In that case, we just divide the entire frequency band into multiple Nyquist zones with bandwidth 1/2T. However, since we assumed improper complex Gaussian, we had what? You now may say that, hey, we have linear, conjugate linear, fresh filtering, right? So we developed a linear, conjugate linear, fresh filter that has interesting structure. Here, this G of T only passes half of the Nyquist zone, in this case, non-negative part of the Nyquist zone. And then we could convert the signal to a vector-valued random process. Then what happened? We could show that this problem, the SISO channel capacity problem, could be converted to MIMO channel capacity problem like this. So here, the original problem looked like that. And here we have what? We put properizing fresh scalarizer and vectorizer. In that case, we have vector-valued input and vector-valued output. So we enclose these things. And then we tried to find the capacity of this channel. And you may say that, why they have the same capacity? Because this P-fresh, properizing fresh scalarizer and vectorizers are invertible transformations. And invertible transformations in the input or at the output of a channel does not increase or reduce the channel capacity. Invertible operations never increase or reduce mutual information. That's why these two, original and this new MIMO model, have the same capacity. And we focused on deriving the capacity of this one, but I forgot about the optimal input distribution of this one, the original channel input, when I talked about the main results of this paper. So you know that, anyway, x of t is what? Is a y-sense stationary vector random process, and also proper, right? Because we already properized. Ready? And the question now becomes, suppose you have some proper complex y-sense stationary vector random process x, and each component is band limited to half Nyquist zone, right? So each frequency component of this optimal vector-valued input random process has bandwidth 0 to 1/2T. Now the question is, what is the property of this random process, scalar-valued random process? So original input distribution. Because That's important in our signal design, and that provides us what must be done in the transmitter. And as many of you remember, what Shannon has found from the capacity problem for band-limited additive Gaussian noise channel, what was the result? What was the input distribution? And some professors never emphasize that question because they, as I did, they were busy in finding the capacity. So let me tell you more about that. So suppose you have a discrete time memoryless channel. So let's see, you have X, you have N, you have Y. And since we have IID observations, the problem is simply input power constraint and noise distribution and the capacity in bits per channel use. So you know this result, right? And here, the question is not only find the capacity, but also what is the distribution of X, optimal distribution of X. What is the input distribution that maximizes the capacity? So for example, suppose we have designed an optimal transmitter and receiver for this discrete memoryless Gaussian, additive white Gaussian noise channel. Now, we do a lot of transmissions over this channel, IID noise, and we may have designed optimal distribution. Now, somebody just watches the input, optimal input that achieves the capacity of this channel. And just he or she tries to draw an empirical PDF. What will be the input distribution? Gaussian. So it's zero mean Gaussian, of course, complex. Okay. So you have not only the real part of X in this complex case, but also the image part. So real of X, you have imaginary of X, IID, and this power P is now serving as the variance of real and imaginary part. So you have circular complex Gaussian noise and circular complex Gaussian input. Got it? Now, let's make a leap of faith and see this one. So you have complex valued random process, now band limited to W over 2, negative W over 2, because we want to have passband bandwidth W, hertz, in real passband. And here we have complex Gaussian noise, proper complex. Just for simplicity, just white Gaussian. Okay, we may find colored Gaussian case, and in that case, we need water filling. And X is, of course, power limited. We need to be careful. Time average. Okay. So again, we can convert this problem to a discrete time additive white Gaussian noise problem by doing what? By doing sampling, uniform sampling. So that is same as here we have some D to A converter, and here A to D converter that optimally converts the signal. So we know that here an optimal distribution of X must not waste power outside this passband of the filter, which means that our optimal distribution must have its discrete time counterpart that can be simply used by ideal D to A converter to construct this continuous time signal. And also, same argument holds there. And after some justification, we can show that this problem is same as what? The use of this channel, discrete time memory channel, at every 1/W second. So eventually our capacity becomes W times log to 1 plus. And here we need to be careful about sigma square and P. So let me not use that one. Power spectral density, if I remember, 2n naught. Yeah, in complex baseband. So we have P over n naught W. Now, bits per second. Something like this. So this continuous time AWGN channel has the capacity formula like this. And here again, there is some person who watches this optimal distribution and describes the property of this optimal input distribution. Then what do you have? You have strictly band limited white Gaussian noise. And since the power spectrum must be matched to the noise, in that case it's again flat, and the height is P over W, so that after integration your power becomes P. So your optimal input is what? Again, white Gaussian noise. And do you see something common in these two problems? So when you have Gaussian noise, optimal distribution is Gaussian. Will it hold even when additive noise is not Gaussian? Of course not, right? Of course not. This optimality of Gaussian input is due to the Gaussianity of additive noise. We may now diverge here. Okay, time's already up, but anyway, the main idea is this. So if you expand this to some frequency selective channel, in that case, what will happen? And also, power spectrum is not flat. What will happen? You have water filling to find the water filling procedure to find the optimal, maximize the mutual information, which is the capacity. And also, your input distribution is not flat in general due to the water filling. It depends on how much power exists in that specific frequency and what is your total power budget, right? However, X of t is still Gaussian. random process, but now colored, but Y-sense stationary. We assume noise is Y-sense stationary Gaussian noise and channel is frequency selective. And we have colored Y-sense stationary input. Now we go back to our problem. And here we have frequency selectivity and we have noise that is cyclostationary. And we can find the solution by converting the entire channel into MIMO channel, and we do water filling over MIMO channel. So we need singular value decomposition, blah, 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 to find parallel Gaussian channels. And now what would be X? X is, of course, Gaussian, random process, Y-sense cyclostationary with cycle period, same as the interference. So that's why Dr. Byung-Woo Khan, my first author of this paper, and me as a co-author, named this water filling procedure to find the optimal solution to this Y-sense cyclostationary Gaussian noise channel as cyclic water filling, because we did water filling, but we eventually have cyclostationary input distribution. So cyclic means cyclic, right? That's why we called cyclic water filling. Anyway, so I'm done for the second take-home exam, which will be given probably today or tomorrow, not later than tomorrow. So due will be Monday, so you may start early. Okay, that's all for today.